So last time we talked about the generalization bound, and today we are going to talk about some better generalization bound for deep networks. So recall that last time what we did was that we showed something like the Rademacher complexity is bounded by something like this. Times some polynomial of the norms of the weights. Right, so, and we said that this comes from a kind of a worst case bound for the Lipschitzness of the model. Of the model. So, and actually this is the worst case Lipschitzness with respect to input. Over the entire, worst case over the entire input space. And this is because when we do the covering number, we have to use this Lipschitz decomposition, this Lipschitz composition lemma. And there you have to use the Lipschitzness for the entire set. Sorry, this is a little bit distracting in the live, just because I'm sharing the screen using my laptop, so that I can charge my iPad. Okay, so and we have discussed a few motivations for us to improve upon these theorems, right? So I guess we discussed 4 of them, and one of them, I guess I'll just briefly mention them in words. One of them is that this bound is exponential in depth, which is bad because typically you have a lot of layers. And another thing is that this is worst case Lipschitzness. And another thing is that typically you want to have something like SGD prefers Lipschitz models. That's good, but this is Lipschitz models, and where Lipschitz is on the empirical data. Because if you think about an algorithm, and an algorithm can only do something on the empirical data, right? So so we'll show this more like later in the course. But even if you think about it, right? So like on the high level, right? So the algorithm can only prefer something about empirical data, but not about the entire space, right? And also we said that for tighter bound, we're going to have something like data dependent, right? Something that depends on the Lipschitzness on the empirical data. So concretely, I guess today we're going to do is that we're going to show something like this. The generalization of parameter theta is a function of Lipschitzness of f theta on the empirical data x1 up to xn, and also the norm of theta. And this function is a polynomial, so that there's no any exponential dependency. There's no product of things. So that's the goal of this lecture. And we're going to call this. So, and we have to we have to define some kind of like, or introduce some new machinery to achieve these kind of things. And the reason is that this is a different type of bound than what we have done before, because you can see that on the right-hand side, you have a function of the training data. So typically on the right-hand side, right? So the so-called, let's call it classical uniform convergence. I guess what really uniform convergence really means, that's slightly kind of debatable because it depends on how you scope it. But at least what we have discussed in this lecture, all the bounds are doing something like this, right? So the bounds before will all look like for every f in some hypothesis class f, the empirical loss is less than something like a complexity measure of capital F over square root, something like this, right? So, or like maybe with high probability, something like this. And alternatively, we can also achieve this kind of things. I think we implicitly discussed this, right? So for every f L of f is less than a complexity measure of little f over square root n. So here this is capital F. So the first type is what we do exactly, what we got exactly from Rademacher complexity, because you just apply Rademacher complexity on it, and this is in some sense the Rademacher complexity. And the second type, you can also get it by doing a little bit things from the first type. So you can get the second type by something like, I guess this is a remark, by considering f to be something like all the functions where the complexity of little f is less than capital C. Right? Think of the complexity as, for example, norm of the weights. Right? You first define a hypothesis class where the norm of the weights is less than capital C, and then you apply 1 on all on capital F on this hypothesis class, and then you do a union bound, and then take a union bound on all C, right? So for every capital C, it defines a hypothesis class. You probably can write it as F, capital F sub C, right? So, and for this capital F sub C, you can do the standard Rademacher complexity, and then you can say that I'm going to enumerate over all possible capital C, and then do another layer of union bound on top of it. We never do this formally, but this is just one parameter. You can just discretize whatever you want. So in some sense, this is how you get the type 1, type 2 bound. But the thing is that either of this bound on the right-hand side, the bound depends on the data, the empirical data. It's always a property either of the model or of the function class. So the question is, how do you, if you want to get something like this, right, like our goal today, you have to do something kind of like more, you have to introduce some new techniques, right? So our goal, right? So our goal is to get something like, I think maybe let's call this, I think we call this data dependent bound, generalization bound. This term might be a little bit kind of overused in certain cases, but what I mean here is that you want to have a bound that with high probability for every f, your population loss is less than some maybe complexity of f and the empirical data. So the right-hand side is also a random variable that depends on the empirical data. Of course, you're asking this for high probability, right? Anyways, right? So you're asking that with high probability over the choice of the empirical data, this inequality is true. And this is useful in the sense that, this is useful still kind of useful in the sense that you can regularize the right-hand side. You can add the RHS as a regularizer, right? So not only this is explanation in some sense, but also it can be used actively as a regularizer, because the right-hand side is something you can optimize, right? So this is kind of the goal that we are trying to achieve. So and in some sense, I think I used to have a little bit argument about why this is actually the right thing to do. It's kind of like tricky because these days still there's no consensus on what exactly kind of generalization bound you are looking for. I believe that this is one thing that is good to have, but but there could be other forms of like generalization bounds. In some sense, you can argue that this is the best you can achieve in the sense that you cannot have a stronger one on the right-hand side, because, for example, you cannot replace this empirical data by population distribution, right? If you replace that, then you can just choose, suppose you allow the complex measure to depend on the population distribution. Suppose you allow that I can have complexity of f and the population distribution p, then why not just define this to be LP of f? Why not just define this to be the population risk? Why, if you allow this, why not just define it to be something like x from p fx, right? So the population risk would be a good complex measure. Then in some sense you lose the the gist here in some sense. It becomes too trivial. And in some sense, that suggests that you are cheating in some sense by allowing the complex measure to depend on P. So in some sense, the kind of the fundamental question we are facing about in the generalization bound is that you don't have access to the population distribution. You want to have an empirical measure for your complexity so that you can use that for regularization. Anyway, but this argument is kind of like anyway debatable. So for now, we just say that this is one of the reasonable goals, right? So, okay, and why doing this is challenging? I think the first thing is that this is challenging because you cannot do the simple reduction as we have done before. So the reduction between 1 and 2, type 1 and type 2 bonds doesn't work anymore. And why? This is because let's give a try. For example, let's define capital F to be all the little f such that the complexity of f x suppose you say this is less than c. Suppose you define this, right? This is your hypothesis class. And let's say, suppose we attempt to use, as attempt is that you use Rademacher complexity for capital F. What's the issue? Why we cannot do this? The reason is that if your complexity measure depends on the data, then your random hypothesis class also depends on the data. Before, your complexity measure doesn't depend on data, your hypothesis class is just a fixed hypothesis class. So now it's a hypothesis class that depends on data. So F is also a random variable, depending on data. Data means empirical data, right? And then you can use the Rademacher complexity, like the theorem for Rademacher complexity, right? Why the Rademacher complexity bounds the generalization error. That theorem requires the capital F to be a fixed hypothesis class that is fixed before you draw the random data. So that's the challenge. Okay. So, and how do we address this? So in some sense, the kind of like the high level way to address it is to kind of like redefine. You have to have a refined way to think about uniform convergence. So some refined uniform convergence. This is not going to be exactly what we do like eventually, because what we do eventually will be something very clean and doesn't have any kind of like a subtlety. But this is kind of the roughly thinking. How do you think about it? So maybe let's make assumption. This assumption is, suppose the complexity measure is separable in the sense that this complexity of F on the empirical example is of some form like G of Fxi, right? It's really some function of F and Xi, and then you take the sum of them. So suppose in this special case, then you can think of essentially what we are doing is that we are considering, then we can consider an augmented loss. So you can define something like L tilde F is equals to something like LF times the indicator that this complexity is less than C. So in some sense, what you are doing here is that you are changing the loss function in some way so that it's easier for you to use the existing bound. So before, for example, let's say the kind of the mental picture I have in mind is something like you have a loss function, which is like something like this. Maybe let's say this is the empirical loss. And you have some region And this is the region where you have low complexity. Right, so but this region is a random region because the low complexity, the definition of low complexity depends on the data, so this is random. So that's why you cannot use the uniform convergence only on this low complexity region, right? So you cannot say that I'm only going to apply my uniform convergence for this region, even though that's your goal, right? But you cannot apply the random macro complexity theory. So the kind of like this kind of like augmented loss, what is fundamentally is doing something like it changed the geometry outside the low complex region. So you for example, you just define the new loss function to be 0 here, and then I like the same thing as it was, in the low complex region. So now you have a globally defined loss function, and so basically the region that you are taking union bound over, right? The hypothesis class is still the same, but you change the loss function. So if you do this, then you can hope to apply like existing tools on L tilde of f, and L tilde of f is sometimes kind of like a filtering thing that filters the low complex region, but you don't do it technically, right? Technically, you are just changing the loss function. That's the only thing you do. But the effect of it is the same as you change the hypothesis class. So I think this is the first thing. Like this is the first attempt that we have done in one of our paper when we try to address this, and this is actually the fundamental idea in some sense. So you change your loss function so that you can deal with different type of quantities or different regions of the hypothesis. And then later, so this is one of the paper we had in, I think, 2019, and we got some results. And if you exactly do this indicator thing, right, you change the loss like this, you can already get something. But kind of the results are messy. So then we kind of like, in some sense, think a little bit more broadly, right? So in some sense, all this is doing is change the loss function, right? So you are trying to have a surrogate loss. And surrogate loss, we are not actually unfamiliar with it, right? We have used the surrogate loss in the margin case, right? It's just the surrogate loss there is kind of like this, the simplest way. The simplest is surrogate loss. So basically what what I'm going to talk about today, in the main part, is this so-called, Euler margin, which is a different way of, it's kind of like a surrogate margin. And once you have this kind of like a fake margin, this is a kind of, in some sense, to define a new loss function for you. And once you have this new loss function, you can do everything in a super clean way. And then you can you can apply the existing kind of tools in some sense. Okay, so this is a kind of like a sketchy, a vague kind of introduction. I'm not sure whether there are any questions so far. Oh, sorry. This is this is the name of the thing we are going to introduce. But we're going to introduce a new margin, which is, we call it Euler margin. Yeah, I probably should define that formally. So okay, so basically the main point I'm saying here is that we are going to define a surrogate loss, and using this surrogate loss, the point of the surrogate loss is to change the original loss so that you can focus on the important part of the space. And this surrogate loss will be basically kind of boring for this kind of like a high complexity part, right? They are not doing anything. They are basically zeroing out, like in some sense. And so that's the general intuition. Okay, so now let's see how do we do that exactly. So we're gonna start with a generalization of margin. So let f so this is a classification model. Right, so typically you just threshold f and get 0, 1, and your margin is just f itself, right? So the typical margin, the standard margin is just defined. The standard margin is just equals to y times fx. Y is between +1 minus 1, right? That's what we used before. And now I'm going to define a so-called generalized margin. We say gfxy is a generalized margin if satisfies the following two properties. So the first property is that gfxy is 0 if you classify correctly. You classify correctly. I think I had a typo here. Let me think. Sorry, I think if you classify wrongly, and this will be larger than 0 if fxy is classified correctly. So let me mark this important typo. Sorry. Okay, so and you can see that this is trying to imitate the standard margin, right? For standard margin, it's bigger than 0 if you classify correctly, and otherwise you say you zero it out. So that's like standard margin. Also, this is only defined for correct classification, right? So in some sense, you can extend to incorrect classification just by extending it to 0, and so. And we say that and there's another small thing, which is that we have to define this so-called infinite covering number. So this is defined to be L infinity epsilon f is this is a small technical extension of the L2 covering number. It's not that important in most of the cases. It just makes in some cases it makes the definition cleaner, and in some cases it makes the proof a little bit easier. So L infinity covering number is the minimum cover size with respect to the matrix rho, where rho is defined to be this L infinity norm. So basically, you say that you look at the entire space of the input of f, and you look at the difference between fx and f prime x, and you take the soup. So basically, this is the f minus f prime infinity norm. Okay, so given this two, what we'll say is that our lemma will be that you can have an analogous theory, analogous to the margin theory, where you use this generalized margin and also the infinite covering number. Actually, you can even do it with L2, like the standard covering number. It's just easier to state with the infinite covering number. And also, maybe before doing that, let me also have another remark, which is that this infinite covering number is larger than the standard L2 covering. This is just because this is a more demanding notion, because you are demanding that f and f prime are closed at every possible input, and before you are demanding that f and f prime are closed on the empirical data, right? So this is because the matrix that we used before was a matrix that is smaller than the matrix used in the infinite case. Okay, so with this small extension, what we're going to do is that we're going to say, actually, you can have an analogous margin theory with the generalized margin. So the lemma is that, so suppose GF is a generalized margin, and let this capital G to be the family of GF, where F is ranging over the capital M. And suppose, recall that this is kind of like what we are kind of like this is in some sense just a slightly kind of like more complex version of your model hypothesis, right? Like if you just use yfx, then this will just be y times fx. That's the hypothesis class. That's the class G. And this is a little bit more general than that. And suppose for some R, the covering number, the infinite covering number of G is less than R squared over epsilon squared for epsilon larger than 0, for any epsilon larger than 0. Right, suppose you have this kind of like 1 over epsilon squared decay in the log covering number. Recall that this is one of the regime that is good, right? So this is actually the worst regime we can tolerate when we do the Rademacher complexity, right? So, and suppose you have this, then with probability larger than 1 minus delta. Delta is the failure probability, which will be hidden in the logarithmic over the randomness training data. For every F in capital F that correctly predicts all training example, right? So for margin, and in the margin theory, we always consider functions that can correctly predict all the examples. Then you have the 0,1 error is less than of tilde of 1 over square root n times 1 over the minimum generalized margin plus O tilde of 1 over square root n. So recall that basically before what we had was, oh, there's an R here, sorry. So before what we had was that here you have the standard margin, the minimum margin over the entire data set. And here R is the complexity of the model hypothesis class, right? And all the other things are the same. Now the change is that now here you replace it by generalized margin, and R becomes the hypothesis, the complexity of the hypothesis class of this generalized margin GF, right? And the complexity is measured slightly differently. We are using the covering number, but actually you can also use Rademacher complexity here. It's the same. I'm just stating it so that it's easier for the future part. And this bound is actually not very tight. You can actually improve this bound, in some ways. But this is the simplest version. And the proof for this, is basically just we just basically reuse all what we have done with margin theory. It's just everything seems to just can transfer exactly. So just to replace, in some sense, the proof is just replace the F by G in the margin theory. I will do this, step by step. But this is a short version. So technically, what we'll do is let's still use the ramp laws. Recall that the ramp laws was the loss function that looks like this. Where this is gamma, right? This part is gamma, this part is 1, something like this. And recall that before, after we have this ramp laws, we define this surrogate laws, right? So we define the surrogate laws L hat gamma theta to be before we just apply the model, but now we use the generalized margin. Before here, this was just f theta, but now it becomes like g of f theta, g sub f theta. And we can also define the surrogate population loss, which is just the expectation of the empirical loss. Okay, so and before what we did is that we use the Rademacher complexity to control the differences of these two loss functions. We said that you take L gamma theta is minus L hat gamma theta is less than the empirical Rademacher complexity of F. That's what we did before, but now it's before we did the empirical Rademacher complexity of L gamma composed with F, and now it's L gamma composed with G, because the function class, the function is different. Plus O to the 4 squared n. Sorry. Oh, okay. Thank you so much. Yeah, thanks. So I will just switch to this. I only have one charger, but yeah. No, I think it's the problem is that when you use this, I cannot charge. Yeah. Right? Oh, but I can wait. It doesn't matter how. Yeah. It's not the charger. It's the plug, the hole. Yeah. Okay. So now it works. Okay. Good. Thanks. Okay. Cool. So. Right. So. Okay. So now we have to use the Rademacher complexity, and then the Rademacher complexity is less than the covering number, right? So I guess maybe let's do the covering number. So covering number. Let's do some preparation. So we assume the infinity covering number, but actually, it's okay. I guess let's say so the covering number, the standard covering number, L gamma composed with G, the L2Pn. This is less than the standard covering number where you use the by removing the L gamma, right? So L gamma, so L2Pn, because this step is using the Lipschitzness of L gamma. So it's actually 1 over gamma Lipschitzness, right? So this is using the Lipschitzness of the covering number. And now, next you say this is also bounded by the infinity version, right? And then in the infinity version, we have an assumption. The assumption was that for every epsilon, this is less than R squared over epsilon squared gamma squared, right? The last step is by assumption. Okay, so you can see that actually, even suppose you assume something about this, then it's also fine if you assume something about, right? So you don't have to literally use the infinity norm. Okay, so and then because this log cover number is less than this, and we have kind of like this kind of like translation, right? So that if you translate log covering number to Rademacher complexity, you got RS L gamma composed with G is less than O tilde R over gamma squared root, right? This is by chaining the Dudley theorem and its consequences, because we have discussed what kind of like cover numbers implies what kind of Rademacher complexity, right? So, okay, so and then the same thing, I guess, take gamma to be gamma mean, which is the min over I, Gi F, and Yi, right? So, and then this step is not formed. There's some caveat here, because gamma is a random variable. You have to do union bound eventually. But let me not get into it. I guess we had this issue before as well. But it's only one number you can discretize and do a union bound over gamma. But suppose, let's say we just take gamma to be gamma mean, and then L hat gamma mean theta is 0. So then you get L01 theta, then 0 plus O tilde of R over square root n times gamma mean plus some O tilde of 1 over square root. Okay. So this proof is not 100% formal just because technically I'm not allowed to take gamma to be anything that depends on the data, right? So I have to really show it for every gamma. And that requires another union bound over gamma. Okay, any questions? So maybe let's see what we have achieved with this lemma, right? What we achieved this lemma is that now if you define your, basically you can fold everything, you can try to fold everything in this generalized margin, right? This generalized margin in some sense is a way to twist your model output, right? So you can stretch the model output for certain f, and you can squeeze it for certain other f. So in some sense, this is what we actually will do, right? So we, in some sense, stretched the function for those places where we'll see, you see how we do it. Like you stretch the function according to where you are at. So basically everything is folded into this generalized margin. And the question is, so the question now is that question, so for what GF, you can bound the generalization error. You can bound the covering number of G, right? And also you want this GF to be somewhat meaningful, so on and so forth. So, and suppose, if you just take GF to be the standard one, YFX, then the covering number of this GF will be the same as covering number of F, and it will be then the Rademacher complexity will be something like then the covering number depends on the product. But we are trying to do better than this. Okay, so how do we do this? So now we define this so-called Euler margin. This is a special instance of this GF. This is a concrete definition of GF for which we can bound the Rademacher or the covering number complexity. So to define this Euler margin, this generalized margin, right? So we have to actually introduce some notations. So we're considering some perturbed model. So I guess, okay, I think, sorry, one moment. Maybe I think actually it's useful to have some motivations before I define it. I forgot to add this. So our motivation is the following. So if you think about the linear model, and the margin is defined to be the margin, the standard margin, right? So this like the normalized margin. So normalized margin is defined to be something like y times fx over the norm of, maybe it says the model is w transpose x. So your margin is defined to be y times the model output over the 2 norm of w, right? So this is the normalized margin, which is something that kind of like governs the generalization performance. And the question is, how do you normalize, right? So like if you have a deep model, then you can try to normalize by something, right? So if you have a deep model, you can, so one attempt is that you can try to normalize by some quantity. Maybe this could be the product of the Lipschitzness, right? Or maybe something else. So that's the natural attempt. And in some sense, all the previous work is in some sense doing this, right? You are normalizing the margin based on the worst case Lipschitzness. So, and what we are doing is that we don't want to normalize by only a constant that depends only on the function class. So we take a different approach. What we do is we say we reinterpret the standard margin by something else. So we have another interpretation. So our interpretation is that you can view this as something like minimum delta such that W plus delta W times x plus delta y is less than 0. So you're trying to find the minimum perturbation of your data point such that after perturbed it, you can cross the boundary, right? So intuitively, this is also kind of right, because the margin is the distance to the boundary, right? So it's also the same thing as how much you can perturb it so that you can cross the boundary. So this is the kind of the perspective we take to generalize the margin for deep models. So if you take this, there's some kind of like a small, like if you do all the exact math, maybe something doesn't match exactly, but this is the kind of like the rough intuition about it. And how do we do this exactly? So for deep models, we are still trying to take this perturbation-based perspective, but we have to perturb. It turns out we have to perturb all the layers, not only the input. So like the first attempt we tried is that you just perturb the input. You try to see what is the smallest perturbation of the input so that you can change the decision of your model, right? But that just technically doesn't work. It doesn't seem to capture the fundamental complexity. So we have to consider this perturbed model that perturbs all the layers. So what we do is we have a perturbation delta, which is a constant sequence of perturbation delta 1 up to delta r, and each delta I is a vector. And the way you perturb is the following. You also have to work out the normalization in the right way. So you first perturb the first layer. So the first layer used to be W1 transpose X, W1 times X in a deep net. And you perturb that by adding delta 1, which is a vector, times the norm of X, a 2 norm of X. And then you perturb the second layer. Okay, how do you perturb the second layer? You first apply W2 on the first layer, on the perturbed version of the first layer. And then you perturb it furthermore with delta 2. And how much you perturb what's the scaling in front of delta 2? Delta 2 is a vector. The scaling is the norm of the first layer. So how do you exactly design this perturbation is a little bit kind of like tricky, right? So like we tried various versions in our research, and it turns out this is actually make everything fit nicely. So you can do this for multiple layers, and then eventually you have this HR, the auth layer perturbed layer, is equals to you first apply the nonlinear the matrix multiplication and nonlinearity on your previous perturbed layer. And then you perturb it by vector delta r scaled by the norm of the previous layer. And after you define this perturbation, you can ask, what's the smallest perturbation that changed my decision? So you can, and that's the definition of the all layer margin, which we call MF XY. This is the all layer margin. It's defined to be the minimum perturbation. And how do you measure the size of the perturbation? You measure it by the sum of the 2 norm of the perturbation on every layer. And your constraint is that after perturb, I guess you call this fx delta. This is the perturbation of the whole model. Fx delta after perturbation times y, it becomes negative, so incorrect prediction. You can also do this for multi labels, but it's essentially the same. So I'm doing binary labels. Okay, so this is the definition of the all layer margin. So you can see that the definition becomes much more complicated, but then the proof of it will be easy. And I guess you can also intuitively interpret this, right? So MFX Y. So in some sense, this is big. If it's hard to perturb, right? So if it's hard to perturb, it's hard to change decisions of the network. And how could it be hard? I think there are the two ways to make it hard to perturb, right? So one thing is that the model F is Lipschitz. And this means that it's very Lipschitz. So this means that you have to perturb a lot to make a big difference of a big change of your model output, right? So, and another possibility is that your Fx just is large. In some sense, your standard margin is large. If your standard margin is large, you have to change a lot, right? You also have to change a lot because before you're outputting something like positive, right? Fx is very big. And now you have to change it to another side of the boundary. So then you have to perturb a lot. Right. So, or maybe I could say F like yfx, y times fx is large. Right? So typically, I always thought about y is 1. So positive means that you are very confident about your prediction, and if you're very confident, then it means you have to perturb a lot, so that you can change your mind, right? So that the model can change its mind. Right. So and here Lipschitz, technically this is Lipschitz in the intermediate variables, intermediate layers, because you are measuring how robust it is to perturbation, but the perturbation is done on the intermediate layers. But the Lipschitz in the intermediate layers, it turns out that it's actually close to Lipschitz with respect to parameters. I'll discuss that in a moment. Okay, so and once you have all of this, so then you have the following theorem. So this is saying that with high probability, L01F, the 0,1 error of F is less than O tilde of the following. You have 1 over square root n first, and then you have sum of, this is the so-called 1-1 norm of W, which I'm going to define in a moment. And also minimum I MF xi yi plus O tilde of R over square root, where is the sum of absolute values bunches of W. I guess in some sense, we are in the mindset that anything polynomial in the norm doesn't really matter, so doesn't matter that much. So this is in some sense you just consider it as polynomial. But of course, you can also talk about whether this 1 to 1,1 norm is the right choice of the norm. In some sense, this is not the best norm we can hope for. So there's still some headroom for improvement here. But I guess suppose you ignore anything polynomial in the norm. So then what's important thing here is this Euler margin here. So basically, this is saying that if the Euler margin is always big, then your generalization is good. If the Euler margin is small, then your generalization is bad. And what's Euler margin? The Euler margin is about the perturbation robustness to the intermediate layers. So this is saying that if you're robust to perturbations in intermediate layers, and that implies that you have good generalization. And you can also compare this with the bound that we got before. You can pretty much argue that this is strictly better than before. So basically, compare. Is this the right place for us to discuss this? I guess let me discuss this, comparing with the previous bound later, when I'm doing all kind of remarks about this theorem. But you can show that this is better than the previous one, mostly just because this MF, in some sense, this MF xy is kind of like, roughly speaking, you can think of this as, so like in the worst case, I think this is smaller. Maybe it's smaller than over fx, something like this, right? So because this is ellipticity and this is how much you have to change your output. You have to change your output from fx to 0, right? So and this is ellipticity, so that's why you have to change. You have to make a big movement to change it, to change fx from something like positive or negative to 0. Wait, my bad. Sorry, my bad. I think I'm doing the, should be this. I said that's why this is kind of better than the previous bound, because the previous bound didn't consider the different preciousness at different data point. But here you are really talking about, if your ellipticity at the data point you have seen, then you can generalize good. Well, but maybe let me discuss this more. I think, let me have a more thorough discussion about this like later. I just don't want to. I want to have show a little bit of this just so that you don't feel like this is a useless bound. But maybe bear with me and just assume this is useful, and then we can discuss all the interpretations. Any questions so far? How well I'm doing on time. Okay, I guess I only have 30 minutes. Okay, so let's just dive into the proof. So I guess the proof requires a few steps, but a few small steps. So first of all, it suffices to bound this n infinity epsilon g by O of this. By the way, I think I have some. Sorry, I think I have some typos here. Don't. I think this should be this. This should be this. I'll double check it later. Because it's always a polynomial, so I didn't really pay too much attention, but I think this is a typo. So I think you only have to show this. Okay. Sorry, I don't know. I don't know really what this. I'll send a script note taker a clarification about this. I think I don't know exactly whether the square is applied inside or outside. But anyway, you have to show some bound like this, right? So let's assume this is the correct bound, and then you basically have to show something like this. Because if you have this, then you can use the lemma before, and then on the generalized margin, then you get this Rademacher complex, this generalization bound. All right, so essentially we just have to bound the covariant number of G. And it turns out that the covariant number of G, you have this very nice decomposition lemma. So let's say let Fi define each layer, the hypothesis class for every layer, right? And we also constrain that Wi 1,1 norm is less than beta I. Okay, so then your IF is really FR composed with FR minus 1 up to F1. This is the notation we have used. And recall that we had a kind of a decomposition lemma before, which was kind of complicated, right? So you have all of these dependencies and how the error propagates. But now the lemma is pretty simple. Cool. So let M composed with F denote its family of the all-layer margin. And then consider, then you have that the log of the infinity covariant number, where the radius is just simply the sum, the average, in some sense a quadratic average of the radius on each layer. And you care about the generalized margin. This is less than the sum of the log infinite norm covering number of epsilon I capital Fi. So in some sense, this is saying that you only have to deal with the covering number for every layer, and then you got a covering number for the composed function class. But you don't get the covering number for the composed function class exactly. You get the covering number of the all layer margin of the composed function class. So, and here, this n infinity epsilon I Fi is defined with respect to the input. So there's an input domain to define this covering number, right? So the input domain x, which is the two norm ball, is less than 1. And so I guess one of the important thing is that this is not F. This is MF, right? This is the all layer margin. Okay, so and the corollary is that if each of the layer you can bound the covering number by something like Ci square over epsilon I square. Suppose you can bound this. Let's use little c here. So then take epsilon to be epsilon times Ci over sum of square root Ci square. Epsilon I is equal to this. Then we have log epsilon. You have the carbon number of the composed model is less than sum of Ci square over epsilon square. So which means that suppose you believe Ci is a complex measure for each of the layer, then you can get the complexity for the composed model, the all layer margin of the composed model. The complexity will be just the sum of Ci square. Yeah, I think I know I didn't have an error here. I think this is indeed something like this. Yeah, this was correct. Sorry. Okay, cool. So, and the Ci will be something like the Wi 1,1 norm, and that's how you go through all these things. Right. So basically, you know, we can show. I think I won't prove this, but this is all because this is for one layer, right? So we assume you can basically, you know, you can believe that you can basically invoke a theorem for linear model to get this. So indeed, it's true. So for linear models, you get something like this. And beta I was the bound on the, so recall that beta I was the bound on the 1,1 norm of Wi. And this will imply the main theorem. Okay, so I hope I convinced you that basically as long as you prove this decomposition lemma, then you are done, because for the right-hand side, you invoke something about linear model, and then you plug in this lemma, you get the covering number bound for the all layer margin, and then you get the original theorem using the lemma I have showed before about the generalized margin. Okay, so any questions so far? Okay, so now let's prove the lemma, the decomposition lemma. So I guess I only state the lemma for the concrete Fi, right, which is the Z mapped to sigma Wiz. you can also have, you can state the lemma in a more general form, and also you can prove it in a more general form. But I'm only going to prove it for this particular family of Fi. And so the first step is that, so we'll show, so there are two steps. Step one, we show that MFX is one Lipschitz in F. And what one Lipschitz in F means is the following. So for every F and F prime, MFXY minus F prime XY is less than, in some sense, the Lipschitzness of every layer. So you have R layers. So this is sum from 1 to R. And you take the max of Fix minus Fi prime X to norm. X is restricted to 1. So here F is equals to Fr composed with Fr minus 1 up to F1. And F prime is Fr prime composed with Fr minus 1, F1 prime. So basically the Lipschitzness of this all-layer margin is something that doesn't have actually a scale in some sense, because you are looking at the this ball with no scale, and also it only depends. It's basically a sum of the Lipschitzness, or the sum of the differences between F1 and F prime. Right? So there's no multiplier here, right? You are not multiplying on the Lipschitzness of F, right? So it's really literally a sum. It's very clean. And let's prove this step one in a moment. But suppose you have step one, then what you can get is that you can use step two. You can use this step one just to get the theorem relatively easily. What you do is you say, now you construct a cover. Construct a cover. And how do you do that? The construction is also kind of trivial. So what you do is you let U1 up to UR be epsilon 1 up to epsilon R cover of F1 up to FR respectively. And recall that, if you still remember what we did last time, the covering was very complicated, right? So you iteratively construct covers and make it, very complicated. But now we just individually construct covers for every Fi. And then we say UI such that UI is equals to the infinity norm covering number, epsilon Fi. And then, so this means that, by definition, right? So we get that, for every Fi in capital Fi, there exists some function Ui in capital Ui such that Fi minus Ui is small, right? So, and I guess we are using this metric, this infinity norm metric, Fix minus Uix to norm is smaller than epsilon I. This is we know by definition. And now we're going to turn this into a cover for the composed family. So, and the cover is just so we just take the U to be the family of just the composition of all of this. The composition of UR composed with UR minus 1, composed with U1, which is and this will be our cover, and we'll show will be our cover for M composed with F. And why that's the case? This is because suppose we are given F is equals to FR composed up to F1 in capital F, then let, I guess, U1 up to UR up to U1 be the nearest neighbor, of fr up to f1. So then, as you can see that using this Lipschitzness, this minus let's say u is equals to ur composed with ur minus 1 up to u1. So you get this. So suppose you do this. This is less than, using our step 1, sum of the difference between fi and ui, the worst case difference between them over the norm ball 1. And because f and ui are close, that's how we constructed the cover. So we get square root sum of epsilon I square, f from 1 to r. Okay. So basically, once you have such a nice Lipschitzness, so kind of Lipschitzness property, then you can just cover everything individually, and you don't have to think too much about the compensation. The compensation is trivial because it's dealt with this. It's dealt with by this. So now why the Lipschitzness holds? So let's prove step 1. So we only prove the upper bound. So we only prove this by symmetry, right? Because f and f prime have the same role, so you only have to prove one side, and you can flip them to get the other side. And in some sense, the way to prove it is just really, each of them is defined by some optimization program, right? And they are the solutions, the optimal value of the optimization programs, right? Basically, you are trying to show that two optimization programs are doing similar stuff. And how do you do that? Typically, you construct the optimal solution of one optimization program into a feasible solution to another optimization program. That's how you relate two optimization programs. So let delta 1 star up to delta r star be the optimal choice of delta in defining MF xy. So, and we want to turn, so our goal is to turn this into delta 1 hat delta r gamma, a feasible solution of MF prime xy. Right, so if it's a feasible solution, you get MF prime xy is less than sum of delta I hat square. And then you can relate this to sum of delta I using your construction. Right, so okay, so that's the rough idea. And how do we construct this delta 1 hat up to delta r hat? So we want it to be feasible so that we can have this inequality, right? This part is going to be the feasibility part. So basically the way we do it is that we want to construct, so we want to make f prime with delta 1 hat up to delta r hat doing the same thing as f and with delta 1 star up to delta r star. So basically you want the perturbation on f prime to do the same thing as perturbation, the perturbation of delta I star on f, so that then you know that this will be a feasible solution. Because what's the feasibility? The feasibility is about whether you perturbed the prediction to the other side, right? So if this one can perturb the prediction, to change the prediction to the other side, then the other one can also change the prediction because they are doing the same thing. That's the principle. And how do you do that? It's just pretty much just algebra. Right, so f has parameter, let's say parameter w1 up to wr, and f prime has parameter w1 prime up to wr prime. And let's consider the computation, right? So I guess the computation is this, right? So h1 is equals w1x plus delta 1 star x. H2 is equals to sigma W2 H1 plus delta 2 star H1, so on and so forth. HR is equal to sigma WR HR minus 1 plus delta R star HR minus 1. So this is the computation you did for, this is the computation for MFXY, right? So, and I want to imitate this computation by perturbing F prime in some way. And how do we imitate that? So the imitation is kind of trivial. So imitate this. So what you do is you say you take, so for F prime, what happens? H1 is equals to W1 prime X plus something, right? Plus, and how do we, so, and you, suppose you predict the delta 1 star X, then it wouldn't help. Because this W1 prime is different from W1, right? So you have to predict something in addition to make this computation the same as before. And how do you do that is you perturb in addition W1 minus W1 prime X. And then these two are literally exactly the same. So basically you declare this as my new perturbation. You declare this has to be my delta 1 hat times X to norm. So basically you compensate the difference between W1 and W1 prime by adding this additional perturbation. So that means that delta 1 hat is equals to delta 1 star plus W1 minus W1 prime X over the 2 norm of X. And you do the same thing basically for every layer. So now H2, you want H2 to be equals to the same H2 above, but your first step is you're only perturbing based on W1 prime. You are not perturbing based on W2. Sorry, you are only perturbing based on W2 prime, but not based on W2. So what you do is you first perturb the original one, delta 2 star H1, and then you compensate the diff by perturbing even more, something like this. And you declare this entire thing will be defined to be delta 2 H1 to norm. And that means that delta 2 hat will be delta 1 2 star plus something like H1 2 norm. And the denominator will be sigma W2 H1 minus sigma 2 W2 prime H1. I guess you do the same thing for every layer. And in general, you just take delta I hat to be delta I star plus sigma Wi Hi minus 1 minus sigma Wi prime Hi minus 1 over Hi minus 1 to norm. And now we got the same, we got our goal. So basically delta 1 hat on F, right, on F prime is the same, doing the same thing as delta 1 up to delta R on F. I'm using this shorthand just to save some time in writing. So I'm saying that basically I'm saying you perturb the delta 1 hat up to delta R hat from F prime. It's doing exactly the same functionality, the same prediction as the other one. So that means that this is a feasible solution. This is a feasible solution for MF prime. So that's why MF prime XY is less than the sum of delta I hat 2 norm square root. And now this is equals to, I guess I'm going to bound this by square root sum of delta I star 2 norm square plus square root sum of the differences between them. And this is using the so-called Minskov, I guess. I always think of it as Cauchy-Schwarz, but I think there's a technical name which is called Minkowski inequality. So what he's doing is that the Minkowski inequality is saying the following. So if you look at square root of the sum of AI plus BI 2 norm square, this is less than square root sum of AI square plus square root sum of BI 2 norm square. So this is the Minkow's inequality. And actually, you can prove this inequality by Cauchy-Schwarz by just you take the square on both sides and cancel a bunch of terms, and it becomes Cauchy-Schwarz. All right. Okay. So we apply this when where AI is delta I star, right? AI is delta I star, and BI is this thing. It's the diff between them. I think 5% is enough for me. Okay. Yeah. Okay. Cool. So yeah, I think 1 minute per percentage. Okay. Okay. So now let's see. So and this one is the MF of XY, and the other one you can bound it by this is, I guess this is literally you can bound this by square root sum over I from 1 to R, the max over X in one norm, and sigma WX minus sigma I prime X square, right? Just because this whole thing is homogeneous, so dividing by the 2 norm is the same as restricting 2 norm to be 1, right? So, and then this is equals to MF XY plus square root sum over R max X 2 norm less than 1 Fi X minus Fi prime X square. And this is what we wanted for step 1. Any questions? W and W prime. So W and W is the parameter for F, and W prime is the parameter for F prime. And they don't have, at least in this context, they don't have any relationship, because I'm just trying to show that, I'm trying to show this step, right? This step 1. So I'm taking 2 arbitrary F and F prime, and I want to say that the Euler margin difference in the Euler margin is bounded by a difference in each of the layers, right? So it doesn't matter what they are. Yes. So F prime involves all the Wi primes, and F involves all the Wi's. Right. Okay, cool. Any other questions?
It feels like this proposition that we just proved kind of motivates MF.
The case again? Okay. Yeah. So this, you know, if I'm guessing the question, I think all of this depends on the definition of MF. Yes, of course. And it's actually, when we do the research, I think it's that we are trying to meet in the middle. Like, you have to change the definition in a way so that the analysis is okay. But in some sense, because the proof is simple and clean, so somehow I feel good about the definition to some extent. Yeah. So I guess I'll use the next few minutes and the 4% of battery to talk about some of the comparisons, interpretations, and possible extensions. So I guess interpretation, I kind of like, in some sense, I've discussed this a little bit. So the most important thing is the Euler margin part. At least that's our man side, you know, and we don't even care about the norm. So you can compare with Bartlett et al. 17. This is the paper that we discussed last time. So you can formally do this, right? You can formally say that the perturbed model, if you look at the difference between the perturbed model and the original model, the difference is something like, if you do some kind of like telescoping thing, this is supposed to be not super hard. So you can basically kind of imagine that for every layer you perturb something, so you pay something like that, and then you have you also have to pay the blowing up factor because of the other things, right? So you can prove this. So if you kind of like ignoring some minor details, which allows me to have a cleaner exposition. So for example, you ignore the dependency on R. Then you can basically say that if maybe let's also suppose y is bigger than 0, just for simplicity, say y is 1. Then basically, if you want fx to be bigger than 0 and fx plus delta to be less than 0, right? That's kind of like what the situation would be, right? Where you perturb your model to predict the wrong thing, and then this means that your delta needs to be basically something larger than the product of the spectral norm, because at least, right? Because that's how you can make enough of a difference, right? So if your delta is too small, then the right-hand side will be too small, so that you don't really make a big enough of difference. So and times fx, right? So so that's it saying that basically, in some sense, this is saying that mf xy over y times fx, right? The new margin versus the old margin, the ratio is something like this. I'm writing this, in some kind of like in somewhat informal way, so I'm ignoring constant or even ignoring some kind of like small minor details. I think this product shouldn't range from 1 to R. It should miss some terms in the middle, but those are not super important. And this is basically saying that if you look at the inverse margin, this is kind of like fx times the product of the spectral norm. So this is indeed a better bound than before, because you are proving our new bound depends on this and the old bound depends on this on the right hand side times the spectral norm. Right. So this is a better bound, at least in this aspect. And another thing is that later. But why this? But why this is how much better it is, right, compared to the previous one? That's a question mark, right? So is it true that your Euler margin now becomes like polynomial instead of like exponential? There are some indicators that this is a much better bound empirically, or conceptually. Empirically, we did verify it seems to be much better. Like the number becomes smaller, just because empirically your ellipticity is better than the worst case bound. And another reason why you can somewhat hope that the empirical this is better is because later we will show. I think I've said this once before, but let me write down again. So SGD prefers Lipschitz solutions, and in some sense on a data point, and Lipschitz on a data point. In some sense, this is saying that your algorithm, in some sense, is minimizing the Lipschitzness on a data point. So that's why your Lipschitzness on a data point is probably better than the worst case Lipschitzness over the entire domain, and that's probably why the gap between these two bounds are significant. So in some sense, you are implicit. So this, in some sense, this is saying you are implicitly maximizing the Euler margin. So, but this, of course, this is approximately because all of this kind of like what SG prefers, in terms of the form, we'll see is similar, but they won't be exactly matching the same form. So we haven't got a fully kind of like coherent theory yet. by conceptually they all seems to roughly match. And another thing is that there's something which actually people actually use in practice, which is called SAM. This is called sharpness aware regularization. This is something that can let you to get better performance empirically on many data sets. And what they are doing is that they are doing perturbation. So we are doing a perturbation, right? But they are also doing a perturbation, but they are perturbing the parameter theta. So they are trying to make this model more Lipschitz in the parameter theta instead of more Lipschitzness in the hidden variable, the intermediate variable HIs. But actually, these two are very related. So here is a fact. If you look at the loss, with the gradient of the loss with respect to the parameter Wi, this is equals to the gradient of loss with respect to. This is on a single example, always on a single example. This is equals to the gradient of the loss with respect to the hidden variables in the layer above and times the hidden variable transpose. So this is just by derivation. Actually this is used to call. I'm blanking on the name. Like in neuroscience, there's actually a term for this thing. But this is just literally just you compute the gradient of Wi. How do you do it? You use chain rule and you get this. So here this is the gradient with respect to hidden variable, and this is the size of the hidden variable. So if you look, that's why if you look at the norm of the gradient with respect to the parameter, then it's quite related to the norm of the gradient with respect to the hidden variable. This is a vector, and this is a matrix. So that's why this is true. So Lipschitzness in parameter is similar to Lipschitzness in hidden variable. It's somewhat related. Okay, so the last thing, I guess I'm running out of time, sorry. So this is a more general version where you don't have to care about the minimum margin over the entire data set. You can prove something like test error is less than 1/√n times, instead of the average, this is average margin, instead of like the worst case margin, the minimum margin over the data set. So you look at the average inverse margin of this form. Square, and then times the sum of complexities of each layer. So, and plus lower order term. Oops, oh really? Oh gosh, we can really. Okay, 5% is not enough. Okay, but this is literally the last thing I want to say. Yeah, but maybe let me. Are there any questions? So basically, the last thing I want to say is that instead of having the minimum like all layer margin there, you can have the average all layer margin. Cool. Okay. Any questions? Okay, I guess then see you next Monday. Wednesday in 2 days. Okay. Wait, today's Monday, right? Okay. Okay. See you. Bye.